Hello everyone, welcome back to Dedikin Cuts. Today we'll be taking a look at a really interesting number theory functional equation question from the Japan Math Olympiad Final Round 2024. Without further ado, let us take a look at this problem. So this is problem 2 from the Japan MO finals of this year. Find all functions f from the positive integers to positive integers such that LCM, which is lowest common multiple of fm plus fn equals LCM of fm plus n for any positive integers m and n. So this looks really complicated, but we will soon be acquainted with this. So let us first take a little moment to try and motivate our solution. Well, as with any functional equation, the first thing you should really check is whether fm equals to m is a solution or not. So in this case, thankfully, if you substitute in fm equals m for all m, you will get the left side is LCM of m, m plus n, and the right hand side is LCM of m, m plus n. So indeed, this is a solution. And the question then obviously is whether are there other solutions. So after trying a little bit of the common type of solutions that you might expect, such as fm equals a multiple of m, maybe fm equals a constant and so on, maybe you are convinced that there are no solutions, no other solutions. So how do we actually prove this? Well, let's now try and motivate the real part of the solution. So usually one thing you want to try with functional equations is also try the small cases. So in this case, you might substitute m equals 1 or n equals 1. Unfortunately, when I tried those out, I didn't really get anything useful. So I'm going to come up with another separate motivating idea. Now, you notice that obviously the functional equations are quite complicated. So maybe you want to get rid of some of the LCMs. So one thing you can do is if you have a fixed m and now you're playing around with n, then if we pick n to be co-prime to fm, then what you notice is that, okay, the two terms in the LCM are going to be co-prime. So the right hand side will just be the product here and you lose the LCM, which is a good thing. And furthermore, this LCM is still quite clunky to work with, but maybe we can extract certain properties from this. So by observing that if this thing is the LCM of the two terms, then individually each of the term must divide the LCM, right? So this means that m divides the LCM, which is this thing. So m divides the right hand side. Okay, this looks a bit more digestible, but the right hand side is still quite clunky to work with. So if again we have a lot of flexibility in playing with n, and n only appears one time here, so that inspires you that maybe we want to play with n such that fm plus n is co-prime to m, then you can basically drop this whole thing and conclude that m divides fm. And this is definitely an expression that seems pretty useful, right? So maybe let us now confirm that we can indeed pick an n that satisfies these two properties. And it's not easy, it's not hard to come up with a construction. So for a fixed m, basically you pick n equals to m minus 1 times fm plus 1. And let's see why this works. Like obviously n is 1 more than a multiple of fm, so n is co-prime to fm. So as before, the right hand side, the LCM just becomes the product, which means m divides the right hand side over here. And indeed, fm plus n is actually, you look at this thing, we add one copy of fm, is m fm plus 1. So this is co-prime to m. So as we desire, this term in the bracket drops out, and we can conclude that m divides fm. And note that this holds for every m, because for each fixed m, we basically choose n in the following way. So this is the first real big observation that we need to make for this problem. And by the way, something really useful to take note of is once we have this conclusion, we also know that fm is therefore greater than or equal to m. That seems pretty useful. And another common fact in number theory that is frequently overlooked but really obvious is that once you are not, if fm is not equal to m, the next multiple is already at least 2m. So this is what I like to call the gap property, right? So you create a gap out of nowhere because you are working with integers and integer multiples. So this is something really useful to keep in mind for number theory problems. And let us now continue our way. So the next motivating idea is we still have a very clunky right hand side to work with, even though we know fm is a multiple of m. So another way we can simplify the right hand side is, what if we select n equals to fm? By selecting n equals to fm, then the right hand side is obviously LCM of fm to fm, which is 2fm. So this looks really simple. Again, we got rid of one of the LCMs, but the right hand side looks really clunky. But thankfully, there's something that we can very quickly observe, which is that this whole chunk here is a multiple of m. Indeed, fm is a multiple of m. A multiple of that multiple is still a multiple of m. You add m, you get a multiple of m. And a multiple of that is still a multiple of m. So in essence, by the first part of the proof, we can conclude that this is divisible by m. So the LCM of m and a multiple of m is just that multiple. So we can totally drop the LCM and all that, and we simplify the left hand side quite a bit to this. Now, the double f still looks pretty annoying. So how do we actually simplify this? Well, before I go into the actual proof, some motivating idea is that we are sort of pre-convinced that the only solution is fm equals to m, right? So what happens if it's not? Then maybe fm is at least 2m, and there's so many f's here, it's likely to blow this up to be something that's bigger than the right hand side. So that inspires you to maybe try to come up with some inequality and show that if it's not fm equals to m, then maybe the left side is bigger than the right side, hence a contradiction, correct? So it turns out that the correct next step is actually not to do the fm not equals to m assumption, but rather first dealing with the double f over here. So we check that if ffm is not fm, what will happen? Well, by the gap property that we observed earlier, this means that ffm will therefore be at least 2fm. Okay, and why is this a problem? This is a problem because let's look at this string of inequalities. The goal is we want to show that the left side will be strictly bigger than the right side, hence a contradiction. So f, this is the left hand side, f of something we saw already is at least that something, right? So now we have this, we plug in our assumption here that ffm is at least 2fm, and then here we see that this is strictly bigger than 2fm. So therefore we have reached a contradiction. Yeah, so turns out that all the inequalities we observed earlier are really useful in proving in getting this contradiction. So this means ffm equals to fm, which is a very good news because you can now simplify this to just a single f instead of double f. And now we basically just play the same game. Now, this time the game we're playing with is, what if f of m plus fn, this left hand side, is basically not equals to m plus fn itself? Then, once again, we know that f of that thing will be at least twice of that thing. And once again, this thing is strictly bigger than 2fm. So again, we get a contradiction. So f of this thing must equal to the thing itself. So very nice. And now if we plug this into the left hand side, we basically get m plus fm equals to fm, which simplifies to fm equals to m. And we can perform this proof independently for each fixed m. So this actually holds or must hold for all m. And we have checked at the start that this is indeed a valid solution. So that is all for this problem. Yeah, so what do you think of this really interesting functional equation problem? I think it is actually quite beautiful. It is not a conventional number theory problem, not your conventional functional equation problem, but it uses very cute little observations and very nifty little tricks. So stay tuned to the channel for more problems and see you soon.